No. In the past we've shown that the way you represent a concept is just as important as the concept itself. Think about the different ways we've represented functions, which have really helped us know how to use functions. So we're now going to talk about a different representation of permutations that gives a great deal of insight into their nature. This is called cycle notation. And it's introduced in this example. Now you see here is a permutation in S6, the permutations on 6 letters. And we know the tableau notation, 1 goes to 2, 2 goes to 3, and so on. Now if you think about this, 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5. I could draw arrows like this. And actually I could put these arrows together. If I put 1, 2, 3, 4, 5, 6. Actually we saw this when we were looking at the roots of unity, and you showed the hexagon, and you showed the hexagon rotating. This goes here, this goes here, this goes here, this goes here. But now we're doing something a little more general, not just in a geometrical context, but any permutation. We can write it this way. We can put the items in the set, arrange, and then we can put arrows to show where they go. Okay, so there's really not a lot new here. It's also similar to what we did in equivalence relations. Now there's more than one way to write such a cycle. We can write this cycle as 1, 2, 3, 4, 5, 6. This means 1 goes to 2, 2 goes to 3, 3 goes to 4, etc. We could also write that as 3, 4, 5, 6, 1, 2. 3 goes to 4, 4 goes to 5, 6, 5 goes to 6. Now the last one here, this 2 has to go back to the 3. That's understood. Okay, so this is a way of representing this cycle here. So there are several ways. Typically we represent the cycle such that the smallest entry is first. And that's the point that's made in this paragraph. Okay. Now think about we can think about some other cases. Here you don't have 1 goes to 2, 2 goes to 3. 1 goes to 3, 2 goes to 4, 3 goes to 5. Now to get this cycle, we'd have to say 1 goes to 3, 3 goes to 5, 5 goes to 6, 6 goes to 2, 2 goes to 4, 4 goes to 1. And then 1 goes back to, and then you repeat again. Okay, so you need to be able to represent permutations both in tableau form like this and in cycle form like this. All right, this cycle form, if I do 1, 2, 3, 4, 5, you can read off 1 goes to 5, okay, 2 goes to 6, etc. Okay, so you should be able to go back and forth between tableaus and cycles. We define the length of a cycle as the number of elements in the cycle. Now, so far we've looked at permutations in S6 and they've all turned out to be cycles. But in fact, that's not always the case. Look at this following permutation. In this permutation, the 1 stays put. 2 goes to 4, 4 goes to 3, 3 goes 2 goes to 4, 4 goes to 3, 3 goes to 2, 2 goes back to 2 again. So we have this smaller cycle, 2, 4, 3, that doesn't involve all of the elements of the set. 5 and 6 also stay put. So here we have a smaller cycle. So if I was going to represent this, if I was going to put the points, I could arrange the points in a circle. 2, 3. Doesn't really matter where you put the points. 5, 6, like that. Now in this case, only 2 goes to 4, 4 goes to 3, 3 goes to 2. And all the others stay put. So in this case, we only have this small cycle instead of a big cycle involving all of the points. Okay. Now, as mentioned here, even if you have 7 points, you may have a cycle that only involves a subset. But when you do in Tableau, when you represent these permutations in Tableau form, you still have to represent all of the elements in the 7-element set. Okay. Now, so far we've seen big cycles and small cycles, and the question is, do all permutations correspond to some single cycle? And in fact, that's not true. And we'll revisit that point in a minute. Now, we know that cycles represent permutations, and we can compose permutations because permutations are functions. So let's consider how to compose cycles. Okay. So suppose I want to compose the two cycles sigma and tau. Okay. This is tau, this is sigma. Now, for instance, I want to know, what does sigma compose tau do to the element 1? Well, you can draw the picture like this. This represents the cycle tau. It's a little bit flattened for convenience. And this represents the cycle sigma. Again, it's flattened for convenience. So I want to know, what does sigma compose tau do to the element 1? Well, let's feed 1 in and see what happens. I know that tau, according to this representation, takes 1 to 2. And then let me just carry 2 over to the sigma, and sigma is going to take 2 back to 1. So if I take tau sigma compose tau, 1 ends up going to 1. Let's just think about what happens if I took 2 instead. If I took 2, 2 would go here to 2 here. And then the 2 goes to 6. And then if I go over here, 6 is not included anywhere. So sigma doesn't do anything to 6. Sigma gets 6 a pass. So 2 would go to 6. And clearly I could do any element this way. Okay. If we did all of the elements, alright, so this is the example that I just showed. If I did all the other elements, you could see in the same way you'd get outputs for each possible input. And you could write down the result in tableau form. Let's think about what the result should be in tableau form. We've done 1, 2, 3, 4, 5, 6. Okay. 3 apparently goes to 2. 5 apparently goes to 3. 6 apparently goes to 5. Let's see what the other ones were. 2 goes to 6, and 1 goes to 1. All right, now it looks like 4 isn't in either cycle, so 4 goes to 4. So I have my total representation in tableau form. I want you to notice something also here, is that we can get the cycle directly without going to tableau form. For instance, here if I found 6 goes to 5, then I can see 5. I can see what 5 goes to 3, and 3 goes to 2. So that means I have a cycle 6, 5, 3, 2. Okay. Now, the way we like to do this is put the 2 first, so that would be the same thing as 2, 6, 5, 3. Okay, so these 3 diagrams illustrate, let's see, just these 4 diagrams illustrate this cycle, 2, 6, 5, 3. All right, some more exercises to play around with. All right, now in this set 1, 2, 3, 4, 5, 6, 7, I could have more than one cycle at the same time. I could have 1, 2 and 5, 6, 7 both operating at the same time. So we're going to investigate that phenomenon in this subsection. 2 cycles are disjoint if their parentheses contain no elements in common. So these 2 cycles are disjoint. If I have, or for instance, 1, 3, 5, 2, 7 are disjoint, but 1, 3, 5 and 3, 4, 7 are not, because they have 3 in common. Okay. Now if you have disjoint cycles, the thing is that whenever you start with an element and see what the successive permutations do to it, if the cycles are disjoint, then any element that's changed by tau is not changed by sigma, and vice versa. Any element that's changed by sigma is not changed by tau. So basically the two cycles are operating independently. We can just write the two cycles together. You can also see that these two commute. If these two cycles are disjoint, then sigma composed tau is equal to tau composed sigma if sigma and tau are disjoint. And that's only if they're disjoint. In general, permutations do not commute. Okay, so we can represent permutation not by some permutations can't be represented by a single cycle, but rather require more cycles. Okay, let's look at this one for an example. If you look at this permutation and try to discover cycles within this permutation, you get 1 goes to 6, 6 goes to 2, 2 goes to 1, so that's a 3-element cycle. You also find, so we've taken care of 1 and 2, now we need to take care of 3. 3 goes to 4, 4 goes to 3, that's a 2-element cycle. And 5 goes to 7, 7 goes to 5, that's a 2-element cycle. So okay, we could write this entire permutation mu as a product of 3 cycles. And as I mentioned before, it doesn't really matter what order you put these cycles in. I could write this as 3, 4, 1, 6, 7, 1, 6, 2, and 5, 7. But we prefer to put the cycles with the smaller numbers first. So we'd put the cycle with a 1 first, then the cycle with the next smaller number second, and so on. Right now, this also gives us a digraph representation. This permutation up here, we could represent in this complicated looking diagram. But if you pull this diagram apart, really you find 1, 2, 3 cycles. So you have a much simpler picture of what permutations do. Permutations just a bunch of cycles together, not just this complicated wishy-washy graph, but we can always turn a permutation into a digraph that looks something like this. Here's the formal proof that the product of disjoint cycles is commutative, as we indicated before. He said if the cycles are disjoint, then any element that's operated on one cycle is not operated on the other cycle. So it doesn't really matter what order you do the cycles in. Okay, and a lot of exercises here for you to practice on. All right, so let's see if we could figure how to do products of permutations directly using cycle notation. Now this should remind you of complex numbers. Remember, complex numbers, we had the Cartesian representation a plus bi, and we had the polar representation r cis theta. And we learned to multiply in this notation, and we learned to multiply in this notation. Multiplying in the polar representation turns out to be easier. And you can argue that multiplication of permutations using cycle notation is also easier than multiplication using tableau notation. All right, so here's an example. Let's try to multiply these two permutations. When I say multiply, I mean compose, because composition is our operation in this particular group of permutations. Permutations always use composition. So if I talk about multiplying permutations, you know what I mean. I really mean composing the permutation functions. All right, so let's get back to this example. I have one permutation here consisting of 2 cycles, another permutation consisting of 2 cycles. And notice that although these 2 cycles are disjoint, this cycle is certainly not disjoint from this cycle. And this cycle is not disjoint from this cycle. So there's a, it really does matter. Mu composed p is going to be different from p composed mu. All right, so let's represent the multiplication. Well, I represent mu composed p as mu is these two cycles and p is these two cycles. So I can feed in any element, see what rho does to it, and then see what mu does to it, and then find the result. For instance, 1. 1, when I put 1 into rho, it's affected by this cycle. 1 becomes 3. It's not affected here. This one takes 3 to 4. So as a result, 1 goes to 4. Same answer as down here. Okay. You can feed in 4 and see the same thing. 4 goes in here. 4 is done. Nothing's done here. Nothing's done here. If I feed 4 into here, 4 goes back to 1. So 4 goes to 1. Okay. So when I do mu composed p, it takes 1 to 4 and 4 to 1. I can do this for any element, and you end up with the cycle 1, 4 and the cycle 2, 6, 7, 3. Okay. So we can actually write that the product of mu with rho is equal to this permutation in cycle notation. Right. And here we have several examples of multiplying permutations in cycle notation. All right, now let's consider permutations in terms of cycles. In fact, when we talk about permutations, all we need to consider is cycles. And this here is a representation theorem. It says we can represent any permutation as a product of disjoint cycles. Or more specifically, a permutation could be the identity, could be a single cycle, or a product of disjoint cycles. And the proof of this theorem pretty much follows this procedure that we've done here with tableaus. When you do a tableau, you know how to use a tableau to get the cycles of the permutation. And this proposition simply formalizes this procedure of taking the tableau, chasing where the element goes, and eventually the element must end up back where it starts. Okay, so I'm not going to go through this in detail, but that's the idea of this proof. Okay, this is called a classification theorem, or I said representation theorem, but it's classification theorem. It says that you can classify permutations, and really what matters about the permutation is the cycles that it can be break up into. If I have one permutation that has one cycle of length 2 and another cycle of length 3 and another cycle of length 7, if I had some other permutation that also has the same cycle structure, in some sense these are the same permutation. For instance, if I have the permutation 1, 2, 3, 6, 7, in some sense that's the same thing as the permutation 1, 2, and 3, 6, 7. In some sense they're the same. They're going to act the same. And of course, if you multiply these together, you get something strange. But if you just consider the behavior of this one permutation, the behavior is going to be very much like the behavior of this permutation. Yeah. And here, in this exercise, you're to list all the possible types of cycle structures or permutations. Okay. Here's an example where if you want the permutations in S5, and you look through this argument and see what possible cycle structures permutations in S5 have. Okay, so there's an argument here for all the possibilities, and these are the possible cycle structures for permutations in S5. Okay, so this really simplifies the picture quite a bit. We have a very much better idea of what permutations look like. And with that, we'll stop this video.